Hello, calculus student. This is section 1.0 lecture. Section 1.0 is our first actual calculus section, and it defines what we call secant and tangent lines, which is what all of calculus 1 is based on. All of calculus is based, well, calculus 1 is based on the tangent line. And in order to understand the tangent line, we first need to know what the secant line is. There are basically 3 homework problems in this section, and they all have to do with secant and tangent lines. 3 homework problems, but they do have a lot of parts, each problem, so just FYI. So definition of a secant line. A secant line to a curve y equals f of x at a point P is a line through P and any other point Q on the curve. So I just drew a picture. You see a curve, the red curve, and I just made up a point P on the curve. And the secant line is just a line that goes through P and then any other point on the curve, which is oftentimes referred to as Q. The word secant comes from a Latin word meaning cut. So you can think of the secant line as being a line that cuts through the curve. And then the tangent line it's basically the secant line that's formed as that Q value that I talked about earlier approaches P. So I'm going to show you a video with much better graphics, but the idea is this, that if we go back to the picture that I drew of the secant line, what you can do is imagine the Q value getting closer and closer to P. So I'm just going to draw my line through Q now. Oops. That's not a great line because it's not crossing P. Okay, so there's my new line as Q got closer to P, right? And then we're going to let Q get even closer to P. Here, I'm going to use a different color just so it gets a little bit, it's messy, but a little bit less messy. So imagine Q getting even closer to P. And then we have something like this. Oops. Like that line. And then imagine Q getting so close to P. So imagine Q getting like so close that we end up with something like this. Like it's so messy, right? And then imagine Q getting so close to P that Q is actually equal to P. And if you can imagine that, what you end up with is something like this, what I drew down here. Tangent comes from a Latin word that means touch. And so oftentimes when we think about the tangent line in calculus, we think about it as being a line that like touches the curve, just like it won't always only touch the curve in one place, but we think of it as being this line that touches the curve. And if you think about like how the word tangent is used in everyday language, like if I say the professor went off on a tangent, like what I'm saying is the professor touched on the subject and then went off and talked about some other stuff. And if you notice the blue line, right, the tangent line, this right here, you notice that it's like it's touching the curve at one point and then it goes off in its own direction. That's the idea. The curve is y equals f of x. So that's the idea with tangent line. I'm going to show you a video. The video is a YouTube video, and I'm like gonna mute. I have it muted. I'm going to talk over it. By the way, I did post the video in modules, like the entire video. So if you do want to watch the video in full, you can go to modules week 2, under week 2, it says YouTube secant line video, and then you can watch the whole video. It's pretty short, but I don't want to use our time watching the whole thing. Yeah, well, it's only 2 minutes, but we're going to watch like 1 minute and I'll talk over it. So in this video, that there's the curve, and then the line that was just drawn, that yellow line, that's the secant line, or that's a secant line through the curve. I believe that the person who did this is thinking of, oh, I'm wrong. The person who did this is thinking of this point up here as the P. And there's the, I'm gonna pause this for a moment. Oh, I can't pause because, I had it on this other thing, but okay, so I'm gonna pause the recording. All right, so going back to this, Q, so we see the secant line, the line that's going through the curve through P and just any other point on the curve, Q. And then notice what's going to happen. So the reason I'm showing you this part of the video is it lets Q get closer and closer to P, like you get to see it happening. So watch. So it actually, just right there, it actually drew the tangent line. So the orange line is the secant line, and then the purple is the tangent line. And now the video is going to show you how that tangent line was formed. Watch Q get closer to P. Watch it. There it goes. It's getting closer. Closer. And you see what's happening to the secant line. It's turning into the tangent line. Q is going to get even closer to P. Watch this. Watch this. And then Q becomes P, and boom, we have the tangent line. That's the tangent line right there. So again, feel free to watch the entire video if you'd like. It's in modules. Right now, we're just going to start some homework. So this is actually, so question 1, it says, it gives us this point. 210, it says it lies on this curve, y equals x squared plus x plus 4. And it says if Q is this point, x, and then the y value is the x squared plus x plus 4, find the slope of the secant line. So it's asking us really to find the slope of a line, just like in algebra, just like in pre-calculus. They give us in the beginning, so you know when you find the slope of a line, or one way to find the slope of the line is to use the slope formula, y2 minus y1 over x2 minus x1. We're going to use that again. They give us our x1 and our y1. That's this point 210. And then our x2 and our y2 will always be this right here. And then like for the different parts of the problem, so just there are 5 parts of the problem. The first 4 parts of the problem, they actually tell you what x value they want you to plug in for your x2. So, the 210, that's your x1 and your y1. And then the 2.1, this is your x2 for this part of the problem. And then to find your y2, we'll have to plug 2.1 into the x squared plus x plus 4. So I'm going to write this on the iPad and we'll work through it. All right, I wrote this all down. And so we have our point that's given to us, our P, 210. And then our other point, Q, is this x squared plus x plus 4. And we are given, for the first part of the problem, we're given that our second x value is 2.1. And so we need to find out what our second y value is, what y2 is, because we're using the slope formula that I boxed in green. So slope formula y2 minus y1 over x2 minus x1. We need all those four values. We have the x1, we have the y1, we have the x2. Now we have to find the y2, and we're going to do that by plugging this 2.1 in for x. So our y2 will be 2.1 squared plus 2.1 plus 4. We're just replacing all of our x's with 2.1. And then I'm going to just enter this in the calculator. And so I'm going to go to Desmos, not the graphing calculator just yet. There's a fly. I'm going to pause and open the window. Okay, the fly is gone. I hate the sound that they make. It just makes it impossible for me. So let's see, I'm plugging in, I'm putting all this into the calculator. So 2.1 squared plus 2.1 plus 4, I get 10.51. So this ends up being 10.51. And this is my y2. And so now I'll plug this, everything into the formula. So I have my y2, the 10.51, minus my y1, which was this 10 up here, over my x2, which was 2.1, minus my x1, which is 2, right? Yeah, my x1 is 2. And so I end up with 0.51 over, that's just 0.1, isn't it? So this ends up being 5.1. It's like, that's the answer. So let's just check it, make sure I didn't make any mistakes. So I get 5.1. And then you would keep doing that for the others. So like for the second part where it says x is 2.01, then this would now be your x2. And then you would plug this in to find out what your y2 is and so on. But there is a shortcut you can use thanks to technology. You can actually, so here's like a shortcut you can use. So you don't have to use a shortcut, but you can. Here's the little shortcut. Since there are so many different parts to this, if there were just one part, then it maybe wouldn't be so efficient to use this shortcut. But for all these parts, I think it's helpful to use the shortcut. And basically what we do with the shortcut is, I'm gonna pause for a minute, erase all this stuff. All right, so here's the idea with the shortcut. So we're given our first point 210, and you can just use this and then apply this for all of the different parts. That's what makes it a shortcut, is that you can apply it for all the different parts. So let's see, we're given our 210 as our x1, y1, and then the x2, y2 is the x, and the x squared plus x plus 4. Those are our x, that's our x2, y2, just in general. And then entering all this into the slope formula, we'll have our slope is our y2, which is this, all of this, x squared plus x plus 4, minus our y1, which is the 10, over our x2, which is just x, minus our x1, which is 2. And then combining our like terms right here, 4 minus 10 gives us x squared plus x minus 6. Is that correct? X squared plus x minus 6 over x minus 2. Oh wow, it looks like this factors, right? X plus 3, x minus 2. This factors, and I can cancel out the x minus 2. Very nice, very nice. So I'm gonna go ahead and factor this. So I have, actually, you know what? I'm not gonna factor it. I'm gonna leave it. There's a reason I want to leave it. So we're just gonna keep it like this. So what you're gonna do, this right here, what I have here, this represents the slope of my secant line. What you want to do is then take this, and this represents the slope for any x, whatever x you want. So we're going to take this and put it in the Desmos graphing calculator, which that's posted if you go to modules, that's posted under the orientation module along with the scientific calculator, but also you can just Google Desmos graphing calculator and it'll come up. And I'm going to enter this slope. So I'm just going to call it y. And I have equals x squared plus x minus 6. And this is all over. To make it all over, highlight the whole thing and then press the division symbol, the per, the slash, and then I have over x minus 2. So one thing I was saying earlier is that this will factor x plus 3 times x minus 2, like the numerator will factor, and then the x minus 2 will cancel out. But one thing is that the graphing calculator doesn't really show you is that right here at the 2, where that point that I'm pointing at right now, the function's undefined right there. The slope is undefined right there, which makes sense because, by the way, it's just the graphing calculator doesn't show you because there's so many points. There's like an infinite number of points on this line, right? And so you can't. I think it's like basically saying it can't really show the whole because the other points are just kind of crowding it out. But there is a hole right there where the slope is undefined. But anyway, I was gonna say this makes sense because if you think about like if we go back to the whole idea of the tangent line, that's the line that's formed as the other point gets closer and closer to your P. And it gets so close to P that you end up with just one point. And we don't have a formula for finding the slope when we just have one point, right? Like it's like if Q is actually equal to P, like what ends up happening is that your ordered pairs are the same. And then your denominator of your slope, the x2 minus x1, it ends up being 0. So that's why there's a hole there. So let's go back. So once you've entered this in Desmos, then what you're going to do is click on edit list right here, and then click on create table, this table. And then what you will do is enter the numbers that they're asking you to plug in for your second x value. So enter these as your x's on the table. So I'm going to enter 2.1, 2.01, 1.9, and 1.99. So they have some x's entered already. Just enter yours, the ones that you're given. And look, when I entered 2.1, look, I get the answer that I got. 5.1 when I did it like the long way, which isn't that long, but when you're doing it for 4 different numbers, it feels quite long. So here, this is much faster, right? What were the other numbers? 1.9 and 1.99. I'm entering these for X, 1.9 and then 1.99. And then we have the 2, which is basically what would happen if Q were equal to P. That's why it has undefined. So here are the answers. The answers are these numbers right here. The 5.1, the 5.01, the 4.9, and the 4.99. So that's the short way to do it, or faster way to do it. If you want, you can also do it the long way, like if that feels more, I don't know, like organic. I don't know if that's the word, but if that feels more comfortable, maybe. And then from there, it says, based on the above results, guess the slope of the tangent line. And the reason they're saying guess the slope of the tangent line is we don't know what it is, because in order to find the slope, we use 2 points and we only have 1 point if we have a tangent line. That's the idea. Q gets so close to P that Q actually becomes P. So, so they just say, okay, well, guess what the slope of the tangent line is based on what we found earlier. And notice that what we found earlier is we're finding, so our P is 2, right? Our X value for P is 2. And we are letting our Q get closer and closer to 2. 2.1, 2.01, that's closer to 2, right? And then we have 1.9, 1.99. And it looks like as you get closer to 2, like from 2.1 to 2.01, you just got closer to 2 there. It went from 5.1 to 5.01. That seems pretty close to the number 5. Same thing with the 1.9, 1.99. 1.9 is close to 2. 1.99 is even closer to 2. And it looks like as we're getting closer to 2, from 4.9 to 4.99, it looks like we're getting closer and closer to 5. So I would put a 5 here. And ta-da! That's what we have. By the way, if we did factor the numerator, what we had earlier, and cancel, like if we did factor this, which we don't have to do right now, but we will later on for like the next section 1.2. But notice this factors x plus 3, x minus 2 over x minus 2. X minus 2's cancel. And now if you plug in 2 for x here, you get 2 plus 3, which was our slope of the tangent line, our guess. So that's how that problem works. Problem number 2 is just like number 1, like you want to work through it the same exact way. Number 3 is a little bit different. What number 3 takes into account is that, so you might have talked about, like in your algebra classes, you might have talked about how slope is the same thing as average rate of change. And yeah, that's the case. So, you know, like math can be used to represent certain situations in the world. We have an X and a Y, and slope, like if we have some situation that that is represented by like these ordered pairs, X, Y, the slope in that situation is thought of as the average rate of change. And same thing here, like slope of the secant line is average rate of change. So like, say for example, I went somewhere, let's say I drove somewhere, and I drove 180 miles in 3 hours, right? Then I would say that my average velocity is 180 over 3, or in other words, 60 miles per hour, right? That would be my average velocity. If I drove 180 miles in 3 hours, my average velocity is 60 miles per hour. Average velocity, that's the same thing as an average rate of change. We're saying that when I say I drove 180 miles in 3 hours, we're saying that my average rate of change of miles per hour is 60. Like every 60, every hour I'm driving an average of 60 miles. That's what that's saying. What the tangent line, so I'm just gonna put another little equal sign here. Slope of the secant line is average rate of change. And with this little example that I gave, it's the same thing as average velocity. So you can have average rate of change of anything that's changing with respect to another thing. So I just gave the example of velocity where we have the number of miles that you're driving is changing depending on how many hours you're driving, right? But you could also have miles per gallon. That's another rate of change, like the number of miles you can drive every time the number of gallons that you put in your car changes, or that you put in your car. Or students per semester or something like that at Laney, right? Like the number of students per each semester that's changing. So it can be like any average rate of change. And so oftentimes like a really common one that we think of just to like kind of get an intuitive meaning of that is velocity. So that's just an example I gave. So I'm gonna just include average velocity as part of this. Average velocity. So slope of secant line, same thing as average rate of change, same thing as average velocity. When we get into the tangent line, though, what happens is that since Q is getting closer and closer to P, you get to find out what's happening right at that instant, right at the whatever that P value is. And so the slope of the tangent line is referred to as the instantaneous rate of change, or the instantaneous velocity. So if I drove 180 miles in 3 hours, maybe my average velocity was 60 miles per hour. But that doesn't mean I was driving 60 miles per hour the entire time I was driving, right? I could have been stopped at a stoplight at some point. So I could have been like at 0 miles per hour at some point. I could have been driving 70 miles per hour at some point. Maybe I was driving 30 miles per hour at some point. Well, definitely I was in order to get up to the 60, right? Or maybe not. I guess we could have started in the middle of my drive, but still my point is that that instantaneous velocity that can give me my velocity like at any point during my drive. Any time during my drive, I can get my like what my actual velocity is at that moment. And that's the slope of the tangent line. So for problem number 3, where we're being asked to find the average velocity, they're asking us once again, to do the same thing that we did in problem number 1, which was to find the slope of the secant line. And then notice at the end of the problem, it says find the instantaneous velocity, or estimate it once again, which means they're asking us to estimate the slope of the tangent line. So one other thing that's a little bit different about this problem is that the setup is different. So they give us this y. So the y, that's like our q y value. And then they say find the average velocity for the time period beginning when t equals 3 and then lasting 0.01 seconds, 0.005 seconds, and so on. So the t equals 3, that actually represents our x1 in the slope formula. And so we actually have to find our y1, and we're going to find our y1 by plugging that in here. So that's one thing. They don't give us our y1 in this case. And then another thing that's different is that it says find the average velocity for the time period beginning at t equals 3 and then lasting 0.01 seconds. So if it's lasting, if you're starting at 3, but then you go 0.01 seconds, your new value, or your Q value, or your X2 ends up being 3.01. So that's just something to be careful of. So like for the next one, your X2 would be 3.005. It's like you're lasting that much time, or the ball, I guess, thrown by the baby alien. Yes, yes. So these are our various X2s, these right here. This is an X2, and then we have another X2, and so on. Okay, let's do the shortcut for this. I'm just gonna do the shortcut because, again, we have a bunch of points. So, and who wants to do all of that by hand? I mean, even with a calculator. Okay, so I'm gonna write this on my iPad. Okay, so I wrote down the function. I wrote down what our x1 is. So here's our x1. And then let's find our y1 first. So to find our y1, we're going to plug in 3 for our t's here. So we'll have y1 is 30 times 3 minus 20 times 3 squared. See, that's 90 minus 20 times 9 is 180. So this is negative 90. Make sure I did that right. 3 squared is 9. I mean, and then 9 times 20 is 180. And 90 minus 180 is negative 90. Okay, so our x1, y1 is 3, negative 90. And then our x2, y2, so our x2 is just going to be just a general, let's just call it x, okay? And then to find our x2, we would basically, I'm sorry, our y2, we would have to plug in this x for all of these, right? But we're just going to make this a general situation here. Y2 minus y1 over x2 minus x1. Using the slope formula. So x2 is x, so y2 would be 30x minus 20x squared. And then plugging everything into the slope formula, we will have our y2, which is 30x minus 20x x squared minus our y1, which was the negative 90, over our x2, which I just called x, minus our x1, which is 3. So this ends up being 30x minus 20x squared plus 90. Oops, 90 over, that's a strange looking 9. Over x minus 3. And I'm just going to enter this in Desmos. So let's go to Desmos graphing calculator. This is x minus 3. And this is negative 20x squared plus 30x plus 90. Did I write it all correctly? Negative 20x squared plus 30x plus 90 over x minus 3. And let's get our table. So we clicked on this little settings symbol, edit list, and then clicked on the little table. This is what I got, but I'm going to enter the numbers that were given. So 3.01, 3.005, 3.002, 3.001. $3.005, I think it was. Yeah, 3.002, 3.001. And then notice what it is at just 3. Undefined, which is what we knew. I mean, we knew because that is our x1, right? And if x1 is the same as x2, then your denominator is going to be 0, which means undefined. So let's just enter our answers. So our answers are these values right here. Negative 90.2, negative 90.1. Negative 90.04, negative 90.02. See, so far so good. Yay. And then estimate the instantaneous velocity when t equals 3. So these numbers, notice they're all getting closer and closer to like the 3.01, 3.01, 3.005, 3.002. Those are getting closer and closer to 3. And so you want to say, okay, if those are getting closer and closer to 3, that means we're creating the tangent line, right? And so what are these getting closer and closer to? And it looks like these are getting closer and closer to negative 90 to me. We started at negative 90.2, then we get negative 90.1, which is even closer, and then negative 90.04, and then negative 90.02. Like these numbers, to me, they look like they're getting closer and closer to negative 90. And so that's my guess. And yay. All right. Have fun with this homework. Take care, everybody. Bye.